everybody, welcome back to another Gregorius Maths video. Today I'm going to be introducing the theta function because A, it's quite an important function in number theory, and B, it's going to be helpful, the property which I'm going to prove, it's going to be helpful in constructing an analytic continuation of the zeta function. Okay, so theta of z is defined as being the sum from negative infinity to infinity of e to the negative pi n squared z. And what we're going to prove is that theta of z to the negative 1 is equal to square root of z theta of z. Okay, so the way we're going to do this is we're going to plug it in, expand the inside with a Fourier transform, and the rest will pretty much do itself. Okay, so theta of z to the negative 1 is equal to the sum from n equals negative infinity to infinity of e to the negative pi n squared z to the negative 1. Okay? Okay, and this equals the sum from n equals negative infinity to infinity of the integral between negative infinity to infinity of e to the negative pi t squared, because it's normal to use t when integrating, or when doing the Fourier transform. Okay, z to the negative 1 times e to the negative 2 pi I n t dt. Alright, now what we're going to do is we're going to do a little substitution. So we still have this sum on the outside. You have the integral between negative infinity and infinity of, well, if we let t equal the square root of z times u, that implies that dt equals square root of z du. Now, the bounds are not going to get changed at all. You can easily verify that. Just plug a negative infinity there and there, blah, blah, blah. Okay. Okay, so we have e, that stays the same, to the negative pi. T squared is z, u squared, and then we have z to the negative 1. Notice that these two will cancel out. Okay, times e to the negative 2 pi I square root of z u n du, and we'll bring this square root of z to the outside. Okay, so maybe you can see where this is going. Okay, now this is equal to the square root of z times the sum from n equals negative infinity to infinity of the integral between negative infinity and infinity of. Now, here's where things get a little bit counterintuitive. Okay, e to the negative, well, of course we're going to get rid of these z's. Okay, they're going to cancel each other out. We're going to bring the two exponents together. That's still fine. Okay, and here's the part that took me a little bit of time to figure out. Okay, it actually turns out, after like wasting 3 pages of my mathematical notebook of ramblings, okay, that actually we have to factor this exponent, e to the negative pi times, and actually we write the inside here as u plus I n square root of z, all squared, du. However, this is not it. When we expand this thing, okay, we're left with u squared plus 2 I n square root of z u minus, because I squared is negative 1, n squared z. Now when we multiply the whole thing by negative pi, well, the signs get changed, okay, leaving us with this. Okay, when we compare to this thing is identical to this, but we have to subtract pi pi n squared z. Now that is the trick. And hopefully now you can see where we're going with this. Because this equals square root of z times the sum from n equals negative infinity to infinity of, well, this thing right here is just a constant. So we can bring it to the outside, e to the negative pi n squared z. Times, and now we have an integral which we should know how to evaluate by now, of e to the negative pi times u plus I n square root of z, all squared, du. Okay, now we're just going to do a couple of substitutions to make this precisely the Gaussian integral. Okay, so we're just evaluating this right now. So the integral between negative infinity and infinity of e to the negative pi times u plus I n square root of z du is equal to, now the integral between negative infinity and infinity of, sorry, forgot to square this. Now we'll let, say for example, y equal this inside. So I have e to the negative pi times y squared dy. Okay, but if y equals, we have this, okay, and now we let sigma equal, actually I never see capital sigma used as a substitution variable. I guess I've probably only seen lowercase sigma because of flammable maths, but anyway, if we let sigma equal, this is equal to square root of pi times y all squared. So if we let sigma equal square root of pi y, that implies that d sigma is equal to square root of pi dy, or that d sigma over the square root of pi is equal to dy. So this is equal to the integral, again, the bounds are never changed, you can check this yourself, of e to the negative sigma squared d sigma, but we have to bring this over square root of pi to the outside. Okay, now this is the Gaussian integral. This right here is equal to the square root of pi. This is, and then we have to multiply by 1 over square root of pi equals 1. So this thing right here equals this integral right here equals 1. So we have square root of z, theta of z times 1. So this thing here implies that theta of z to the negative 1 is equal to square root of z, theta of z, and goodbye.